Welcome to the SAR channel, where sound and audio are demystified. When you hear a guitar string, can you tell its seventh harmonic apart from the main note? Can you hear the difference between tones at 1000 Hz and 998 Hz? Psychoacoustics studies how we perceive sound, how our ears and brain respond to it. It connects the physical and scientific aspects of sound with our psychological and emotional reactions. In the end, what matters most is how we actually hear and feel sound. The ear and nervous system form a highly complex and sensitive mechanism. It can notice tiny changes or flaws in sound, but it also ignores some details completely. This means some parts of a sound can be recorded or encoded less accurately without affecting what we hear. However, how much accuracy can be lost depends on frequency and time. Both ears are physically similar, but the two halves of the brain process sound differently. The right ear connects mainly to the left brain, which handles speech and language, while the left ear connects to the right brain, which processes music and melody. So, we usually understand words better through the right ear and music better through the left. Engineers can measure sound intensity objectively, but psychoacoustics also considers how loud a sound feels. Intensity is a physical measure. Loudness is how we perceive that intensity, depending on both frequency and volume. Loudness can't be measured by machines. It's judged by listeners. The ear can handle an extremely wide dynamic range, from the faintest whisper to painfully loud sounds. A 120 decibels SPL sound is about 1 trillion times stronger than the quietest audible sound. The ear is so sensitive that at 3 kHz, a barely audible sound moves the eardrum by only 1/10 the diameter of a hydrogen atom. Because of this huge range, we measure sound in decibels, a logarithmic scale. The ear also adapts very quickly. Within half a second, it can shift from hearing the loudest sound to detecting the quietest. Unlike the eye, which adjusts slowly to light, the ear works almost instantly across its full range. It can even detect a sound gap as short as 1/500th of a second, making hearing one of our sharpest senses. Still, hearing sensitivity changes with frequency. The ear is most sensitive between 1 kHz and 5 kHz, and less so at very high or low frequencies. Frequency is an exact physical measurement, while pitch is our subjective perception of it, influenced by frequency, loudness, and waveform. The ear also responds to frequency changes logarithmically. Our brain locates sounds using cues like timing, loudness differences, and waveform shape. When sound comes equally from two speakers, we perceive it as coming from the middle, an illusion created by the brain. Stereo sound, in fact, is just two mono signals that our brain combines into a 3D experience. The ear only perceives a small portion of the total data in an audio signal, called perceptual entropy, roughly 1.5 bits per sample. Signals with less perceptual entropy can be compressed more efficiently than complex ones. Audio codecs use psychoacoustics to remove parts of the sound we wouldn't notice, reducing file size without reducing perceived quality. The process is called data reduction, and though the original signal isn't perfectly restored, the difference is often inaudible because only irrelevant data is removed. Traditional audio designers focused on objective specs like flat frequency response or low noise. But psychoacoustic-based design centers on the human ear itself. Modern perceptual codecs and systems aim to match how we actually hear, proving that sound, whether analog or digital, is ultimately a subjective experience. The ear works through a complex mix of mechanical and nerve processes. It changes sound waves, acoustic energy, into mechanical vibrations, and then into electrical signals that travel to the brain, where we recognize and interpret the sound. When a pure tone is mixed with noise, only the parts of the noise that are close in frequency to that tone can hide or mask it. Sounds far from that frequency don't matter. This specific frequency range around a tone is called a critical band. These bands are narrower at low frequencies and wider at high frequencies, meaning the ear can pick up more detail at low tones than at high ones. Most modern audio codecs take advantage of this by using amplitude masking within critical bands to hide unwanted coding noise. This allows them to use fewer bits without reducing how good the sound seems to our ears. Experts in psychoacoustics note that critical bands also affect how we perceive pitch, timbre, phase, and speech clarity. They help shape our overall experience of sound. Critical bands are vital in perceptual coding because they show how the ear separates sounds that fall inside a band from those that fall outside it. This difference is what makes masking possible. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Two key ideas explain how we hear: the threshold of hearing and amplitude masking. The threshold of hearing shows the quietest sound we can detect at each frequency. Our ears are most sensitive between 1 kHz and 5 kHz, where we can hear sounds even below the 0 decibel reference level. Sounds at very low or very high frequencies must be much louder to be heard. For example, a 20 Hz tone needs to be about 70 decibels louder than a 1 kHz tone to be just audible. In perceptual audio coding, signals quieter than this threshold are ignored since the ear can't hear them anyway. Similarly, quantization noise that stays below the threshold is inaudible and can be safely removed. When two sounds occur together, amplitude masking happens. A loud sound can hide or mask a softer one. This raises the hearing threshold around that sound's frequency. The masking threshold marks the lowest level where a sound can still be heard. Just because a sound exists doesn't mean we hear it. Sometimes one sound prevents us from hearing another. The loud sound is called the masker, and the softer one is the maskee. The softer sound is only heard if its energy matches that of the masking sound within the same critical band. Perceptual codecs use this principle, letting the music signal hide the coding noise if both occur in the same band at the same time. Low frequencies can mask higher ones, and masking can even spread across nearby critical bands if a sound is loud or rich in harmonics. Quiet or narrow band sounds, like sine tones, cause very little masking, while louder or more complex sounds cause much more. Masking curves are uneven. The masking effect extends farther toward higher frequencies, meaning a low tone easily hides a higher tone, but not the other way around. Weak maskers only affect a small range of frequencies, while stronger ones widen the masking area, especially on the higher side. The ear can tell quiet sounds apart more easily than loud ones. In perceptual coding, engineers focus on keeping quantization noise hidden by tonal or noise-like signals. Music can be both tonal, clear notes, and non-tonal, noisy textures. And psychoacoustic models treat them differently because each masks sound in its own way. Pure tones offer the least masking, worst case, while complex sounds provide stronger masking, allowing more efficient compression without losing perceived quality. Amplitude masking happens when sounds occur at the same time, but temporal masking happens when sounds occur close together in time, though not simultaneously. A sound can be hidden by another sound that comes before or after it. When a softer sound is hidden by a louder sound that appears after it, it's called pre-masking or backward masking. When the softer sound is hidden by a louder sound that comes before it, it's called post-masking or forward masking. In both cases, the closer the two sounds are in time, the stronger the masking effect. Just like amplitude, masking gets stronger when two tones are close in frequency. The length of pre-masking doesn't depend on how long the masking sound lasts. But post-masking fades more quickly when the masker is shorter or quieter. A tone is more easily masked by an earlier tone if they are close in frequency, or if the earlier tone has a lower frequency. If the masker is at a higher frequency, post-masking is weak. In general, simultaneous amplitude masking is stronger than either pre- or post-masking because the sounds overlap completely in time. Temporal masking plays an important role in frequency domain audio coding. These systems process blocks of sound samples, which can cause quantization noise to spread over time. Temporal masking helps hide this unwanted noise, especially during short, sudden sounds called transients that might otherwise create a pre-echo effect. Both amplitude and temporal masking together create a time-frequency pattern, or masking contour. Any sound that falls below this contour is inaudible because it's masked. The job of perceptual codecs is to detect this shifting contour as the signal changes and compress the audio accordingly. Even though a masked sound physically exists in the signal, our ears simply don't perceive it. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Psychoacoustic models imitate how the human ear and brain process sound. They study the frequency content of an audio signal to figure out how to compress it while keeping any added noise inaudible. Most models calculate masking thresholds within critical bands, the limits where small amounts of noise can go unnoticed. For each small time block or frame of sound, the model decides how much coding noise can be tolerated in each band. The difference between the loudest signal level and the quietest audible level, the signal-to-mask ratio, or SMR, determines how many bits are given to each band. The model also checks how tonal or noise-like a sound is, because that changes the shape of the masking curve. Each model must also be time-aligned with the audio data so that analysis matches the correct section of sound, accounting for filter delays and block timing. In most codecs, the goal is to make the noise-to-mask ratio, NMR, as small as possible across each frame. The total bits used for encoding can't exceed what's allowed by the chosen bit rate. SNR, signal-to-noise ratio, measures how much stronger the signal is than the quantization noise. Using more bits for quantization increases SNR. SMR, signal-to-mask ratio, is the difference between the masker level and the masking threshold within a critical band. It shows how many bits are needed for accurate encoding. If a signal falls below the threshold, it doesn't need to be encoded. NMR shows how close the quantization noise is to becoming audible. If SNR is greater than SMR, the noise stays hidden. If it's smaller, the noise can be heard. The codec adjusts bit usage to keep NMR low and maintain high sound quality. When NMR is below 0, the coding is effectively transparent, no audible loss. When it's above 0, you can hear degradation. The masking threshold itself changes depending on whether the masker's sound is tonal or non-tonal. The codec must always keep the noise below the just noticeable distortion, JND level, or more precisely, below the threshold of hearing. The success of a perceptual codec depends heavily on how accurate its psychoacoustic model is. But what truly defines quality is how the model's results are used during bit allocation and quantization. The relationship between the model and the quantizer is the most complex and often the most secretive part of any codec's design. Many psychoacoustic models use a spreading function to calculate how sound energy is perceived by the ear. It's easy to estimate masking within a single critical band by measuring the energy of a tone inside that band. However, masking doesn't stop there. It also affects nearby bands. The spreading function explains how this masking influence spreads across several critical bands. To apply it, the audio spectrum is first divided into separate critical bands, and the energy in each one is measured. These energy values are then adjusted using the spreading function to form the auditory spectrum, which represents how the ear actually perceives sound. Finally, by including offsets and the absolute threshold of hearing, the model determines the final masking thresholds, the levels below which sounds are no longer audible. Distinguishing between tonal, pitch-based, and non-tonal noise-like sounds is a key part of most psychoacoustic models, since each type affects masking differently. Noise masks other sounds more effectively than pure tones do. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.